So that balanced chemical equation gives us the relationship between molecules, right? This says 2 molecules of octane combined with 25 molecules of oxygen to produce 16 molecules of carbon dioxide and 18 molecules of water. Well, that's going to be a reaction on an extremely small scale because atoms and molecules are far too small to see. So we can also express this in terms of moles. Moles are the chemist's dozen, right? So if 2 of these react with 25, then 2 dozen would react with 25 dozen, right? Or 2 moles of this would react with 25 moles of that. And that's more useful because 2 moles of something is a quantity that you can see, right? It's actually a quantity that's manageable. We looked at a mole of water as like a tablespoon of water, right? Nice amount. So we can interpret these chemical equations in terms of particles, molecules or atoms, or moles. So the coefficients in a chemical equation specify the relative amounts in moles for each substance involved in the reaction. Any questions? So the amount of substance used and the amount of substance made is related. So we talked about the law of conservation of mass. We can't have mass being created or destroyed. And so we can get a relationship between the reactants and products. And this is called stoichiometry. It's looking at the numerical relationships of chemical quantities in chemical reactions, stoichiometry. You've heard of that, good. You should have heard of that. Chem 3A or high school chem or whatever your prerequisite was. So let's switch from combustion of fossil fuels and talk about making pizza. Oops. So a recipe is something like a chemical equation. So here's a very simplified recipe. 1 crust plus 5 ounces of tomato sauce plus 2 cups of cheese makes 1 pizza. Okay? And we can express that relation mathematically. I know, we're taking fun pizza, yummy food, and we're making it into math. Yeah. 1 crust to 5 ounces to 2 cups to 1 pizza. We can express that in terms of ratios. And we can use those ratios to figure out how many pizzas we could make from 10 cups of cheese. Now you can figure that out without doing math, although you're doing the math in your head. But with this thing that we can understand, let's look at the process so that we can apply the process to something that doesn't make any sense. So if I have 10 cups of cheese, and I want to know how many pizzas I can make, I can use dimensional analysis, and my conversion factors are going to come from this equation. So I have cups of cheese, I want to know pizzas, so I'm going to have 1 fraction here, and I'm going to have pizzas on the top, and I'm going to have cups of cheese on the bottom. And I'm going to do it that way so that the units cancel out. You with me? This relationship here comes from the balanced equation or the recipe. This tells me there are 2 cups of cheese needed for every 1 pizza. So 1 cup of pizza is equivalent to 2 cups of cheese in this process. Does that make sense? So I put the numbers in based on where the units are, and then I do the math. 10 times 1 divided by 2, 5 pizzas. Right? Any questions? So we can do a very similar thing using moles of compounds in chemical reactions. The conversion factors come from the coefficients, And we don't have to do multiple steps. We can choose any two reactants or products because all of those are related. So let's look at this one. If we burn 22 moles of C8H18, how many moles of CO2 form? So we're starting with moles of, let's just use the abbreviation, moles of C8H18, and we're trying to find moles of CO2. I can do that in one step. I find it useful to use this chemical equation to organize the information. This one's pretty simple, but they're going to get a little more complicated. So this is telling me I have 22.0 moles of C8H18. So that's this guy right here. So I'm just going to write underneath 22.0 moles. And then it's saying how many moles of CO2. So under CO2, I'm going to put a question mark, moles. I've got this info. I need to find this one. I can go from there to there in one step. I don't have to go through oxygen because 2 moles of octane would form 16 moles of CO2. So 22.0 moles of C8H18. We can't just write mole because we've got moles of CO2 and we've got moles of octane. And we need to know which mole we're referring to. So I'm going to have a fraction, and I'm trying to go to moles of CO2, so I put moles of CO2 on top, and moles of octane on the bottom. This is exactly what we did with the pizza and the cups of cheese. The moles cancel out. And then I'm going to look at the coefficients here. 2 moles of octane to 16 moles of CO2. So there's a 16 in front of CO2, I put 16 in front of moles CO2. There's a 2 in front of octane, I put the 2 in front of moles of octane. Now yes, you could simplify that to 8, but you're going to use your calculator anyway. Yeah?
Is that supposed to be like a ratio?
It is a ratio, yes. It is a conversion factor. All conversion factors are ratios. What's important about them is what's on the top is equivalent to what's on the bottom. So for every 2 moles of this, I get 6 moles of that. That's true for this chemical reaction. It's not true for everything. So I've got 22 times 16 divided by 2. $176. And the unit would be moles of CO2. Any questions? Do these numbers have significant figures, or are those exact numbers? They're exact, because this is talking at its root about 2 molecules of this and 16 molecules of that. And so those by def are counting numbers, right? And so these coefficients, the mole ratios, are exact numbers. 22.0 moles, that's measured, that's not exact. That has 3 significant figures, and so my answer has 3 significant figures. Of course, we don't measure things in moles, we typically measure things in grams. And so we have to add some conversions onto what we just did. This is the general plan or path for stoichiometry. Grams to moles to moles to grams. So the mass of A, usually in grams, and you can convert that to the amount of A in moles. We've learned how to do that, use the molar mass, right? Amount of A in moles to amount of B in moles, that's what we just learned. Coefficients from the balanced chemical equation. And then moles of B to grams of B, again, we're going to use a molar mass. So grams to moles to moles to grams. There's moles in the middle. And there's usually moles in the middle. So this is your starting point for all stoichiometry problems. Grams to moles to moles to grams. Any questions? So let's do an example related to that greenhouse gas problem. Lots of words here. According to the U.S. Department of Energy, the world burned 3.3 times 10 to the 10th barrels of petroleum in 2013, the equivalent of approximately 3.7 times 10 to the 15 grams of gasoline. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. So this is that same chemical equation we've been looking at. And then we're going to compare the result of that to what volcanoes put off. Volcanoes produce about 2 times 10 to the 14 grams of carbon dioxide in a year. So, lots of words, lots of numbers. We always need a balanced chemical equation, and we can use that to organize the information. This barrels of petroleum. Do we necessarily need all the numbers? We don't. I mean, that's interesting, but they're saying this many barrels of petroleum, which is equivalent to this amount of gasoline. So those things are pretty much the same. The one that we're more interested in is this one. And we're going to use combustion of octane to represent the combustion of gasoline. So you can see that all of this is very much estimating and approximating, right? So this much gasoline, and to simplify things, we're going to say, well, it's just octane. So that's our quantity of octane. 3.7 times 10 to the 15 grams. Now, what are we trying to find? Mass of CO2. So over here, CO2, I'm going to put a question mark. And the mass, probably grams would be an easy unit. So I'll put grams. So we need a path. We can't go from grams of octane to grams of CO2 because the equation doesn't give us that relationship. It gives us relationships between moles. So we're going to do grams to moles to moles to grams. Grams of the octane to moles of octane to moles of CO2 to grams of CO2. Grams to moles to grams. Any questions? We only have to involve the compound that we're given information about and the compound that we're trying to find information about. We don't have to do anything with the oxygen or the water. They're just sitting there. So that's my path. That's my blueprint for this whole calculation. So 3.7 times 10 to the 15 grams of C8H18. This is dimensional analysis. This is why I tried to make you learn dimensional analysis earlier, because it makes these calculations so much easier. So if you haven't figured it out yet, pester me with questions until it makes sense. I'm just going to use these to tell me what goes in the numerator. I have 3 arrows. I'm going to have 3 fractions. Grams of octane to moles of octane. Next is moles of CO2, and then grams of CO2. I'm going to take the previous unit and bring it to the denominator of the next term so that those units cancel out. So those cancel. And these cancel. And these cancel. Okay? All the units in there first. Then the units tell us where to put the numbers. Grams to moles. What's the conversion factor for that? Molar mass. So we're going to have to figure those out. This one in the middle, moles to moles, where do the numbers for that come from? The equation. Oh, well that's easier. So I like to just get this one out of the way first. This is telling me 2 moles of octane for 16 moles of CO2. So CO2 is in the numerator, so I'm going to put the 16 with the CO2 and the 2 with the octane. It is just as simple as taking this 2 and putting it in front of that, the same symbols. And take this 16 and put it there. Now we have to calculate some molar masses. So for octane, I need 8 carbons and 8 hydrogens. No, 18 hydrogens. One 114.224. Generally, the number that you're starting with, the mass that you're starting with, is going to limit your number of significant figures. So as I've done this would only have 4 significant figures, but there's only 2 more. I might as well just write them all in. That's kind of my feeling. It's not going to matter. It's certainly not going to hurt. And that would be 1 mole of octane. And then we do the same thing for carbon dioxide. We've got 12.01 plus 2 times 16. 44.01. This time grams is on top. That's where the number goes. 44.01 grams to 1 mole. So I had this path, grams to moles to moles to grams. I used that to write out the main structure of my equation. The units then told me what numbers I needed and where to put them. Now I'm going to get out my calculator and I'm going to put in this number, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, and just go across. And I'm getting a very big number. So I'm going to put it in scientific notation. 1.140. So this should have 2 significant figures. 1.140 times 10 to the 6th grams. So when rounding that, I'd call that 1.1. Yeah, thank you. I'm like, that's not nearly enough. I messed up over here. I lost my 1. So good to check your math and, go back and look at what you wrote. So I think that ends up, maybe somebody else can do the calculation. I think it comes out to 10 to the 16.
Yeah.
Thanks. So 1.1 times 10 to the 16th grams of CO2. That's our estimate of CO2 into the atmosphere from combustion of fossil fuels. Well, how does that compare to what volcanoes produce? Well, they're both really big numbers. Can't remember what's on the next slide. Yeah, okay. Let's compare them. So this one's smaller than that one. So let's take the larger one and divide by the smaller one. So 1.1 times 10 to the 16th grams divided by 2 times 10 to the 14th grams. The grams are going to cancel out. and I get 55. That tells me that petroleum combustion puts 55 times more CO2 into the atmosphere than the volcanoes do. So it's probably not volcanoes causing the increase in carbon dioxide. This does not prove that fossil fuels are causing global warming. There's just so many different factors to consider that even the best scientists disagree about a lot of this. Any questions? So I won't test you on global warming, but you should be able to do a calculation like that, okay? Let's do another one. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl, according to this reaction. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? Lots of words in there. What we're interested in are the numbers. So we read all the words, and then we go back and pick out the numbers. And so here we've got 3.26 grams of magnesium hydroxide. So I'm going to write that mass underneath the chemical formula in that equation. And then I want to find out what am I trying to find? Here's the question word, what? What mass of HCl in grams? So I'm trying to find HCl in grams. HCl is my other reactant. Question mark. Grams. Now the previous example we looked at the relationship between a reactant and a product, but you can also look at the relationship between two reactants or two products. Any questions so far? What's my generic stoichiometry path? Grams to moles to moles to grams, right? So I'm going to write that up here. Grams, what am I starting with? Magnesium hydroxide. So grams of magnesium hydroxide, yes, it's a little tedious to write the formula over and over again. 2 moles of magnesium hydroxide. 2 moles of what? What? HCl, the thing I'm trying to find. And then 2 grams of HCl. I don't have to do anything with the other with the products. Just the 2 things that I'm interested in. The one I've got information about, the one I'm trying to find. So I've got my path, I can write out my equation. 3.26 grams of magnesium hydroxide. 3 arrows, 3 fractions. So this is moles of magnesium hydroxide. Next is moles of HCl. And next is grams of HCl. And then bring the previous unit down here so it cancels out. These cancel out, and moles of HCl, those cancel out. This is the hard part, just getting the overall idea, where am I going? I'm going to get there. Once I have this in place, this is just following a pattern. It might be a little tedious, but I just need to write stuff down. So I need 3 different numbers here. I like to do the moles in the middle first because they're easy. What number should I put in front of moles of HCl? 2, because that's the coefficient in the balanced chemical equation. And what goes in front of moles of magnesium hydroxide? 1. There's no 1 here, but we understand that there's a 1, and I could leave this blank down here understanding that there's a 1. So now I need molar masses for these compounds. Calculating molar masses is something we do a lot. So magnesium, 24.35? 31. 24.31 for magnesium. The OH is in parentheses with a 2 on the outside. That means there's 2 oxygens and 2 hydrogens. So plus 2 times the mass of oxygen and 2 times the mass of hydrogen. Bless you. $58.326. Sig figs tell me this would only have 4 significant figures, but how many does my starting number have? 3. So is this number going to limit the number of sig figs in my answer? No. It should always end up that these numbers do not reduce the number of significant figures. The mole ratio is always exact. So I guess what I'm saying is that most of the time, especially if you hate sig figs, most of the time what you can do in stoichiometry is whatever number of sig figs you're starting with here, that's how many you'll end with, and just don't round stuff off too much in the middle. You'll be fine. HCl, 1 hydrogen, and 1 chlorine. 36.458. So 36.458. 3.26 divided by 58.326 times 2 times 36.458. 4.07. Write down 2 extra digits. 4.08 grams of HCl. Any questions? Let's do one more, and then we'll call it quits for today. A component of acid rain is nitric acid, which forms when NO2. Also, pollutant reacts with oxygen and water according to the simplified equation. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year, assuming that there's adequate O2 and H2O. What mass of HNO3 in kilograms can form from this amount of NO2 pollution? Lots of words. When I was in school, we called these story problems. Right? That's friendlier sounding than word problems. Life is full of word problems. Anything practical is a word problem. So we always need the balanced chemical equation. So here, I'm planning ahead, and I've written it out, and I've left myself some space. When you're doing a problem like this, if it's like on mastering chemistry and you're writing everything down, you got to write the balanced chemical equation out. If it's like on an exam or a worksheet and it's already written for you, just use it. But use that to organize the information. So I've got all these words. There's actually only one number, 16 kilograms, right? So that must be important. 16 kilograms of NO2. So I'm going to write that here, 16 kilograms of NO2. And then it's asking me, what? What mass of HNO3 in kilograms? So I'm trying to find HNO3, so there's my question mark, And the requested unit is kilograms. Well, our general thing was grams to moles to moles to grams, right? Grams of NO2 to moles of NO2 to moles of HNO3 to grams of HNO3. Yeah, we're going to have to do grams to kilogram, right? And kilograms to grams. So we can take this and we can add a step in the beginning and do kilograms of NO2 to grams of NO2. And then we could add another step at the end where we go grams of HNO3 to kilograms of HNO3. So grams to moles to grams is the starting point. Sometimes you don't need the whole thing. Sometimes you need to add some stuff on each end or one end or the other, but it's our starting point. So there's our path. There are simpler ways to do this, but this is the most straightforward, and we're just going to go for it. And we're going to have to write small to get this all in one line. So I've got 16 kilograms of NO2. And on the next line, I'm going to have grams of NO2. And the next one is moles of NO2. And the next one is moles of HNO3. And then grams of HNO3 and kilograms of HNO3. So I took these terms and they are in my numerators. There's no thinking involved here, just copy them down, right? Follow the pattern. Sometimes you overthink things and then you screw it up. Just follow the pattern. I'm going to take this unit and put it down here. I'm going to take that unit and put it down there. This unit and put it down there. Because that's how I get the units to cancel out. Kilograms of NO2. Those cancel. Grams of NO2. Those cancel. Moles of NO2. Those cancel. Moles of HNO3, those canceled. Grams of HNO3, and those cancel. Right? So many units, right? Now I need numbers. I always go for moles first. Moles to moles. 4 moles of NO2 makes 4 moles of HNO3. 4 and 4. Could you cancel out the 4s? Sure. Write them in there anyway. And then I need some molar masses, right? I need the molar mass of NO2 for this term. I need the molar mass of HNO3 over here. So I'm going to have to calculate those. So HNO3 is H plus N plus 3 O's. I'm doing the second one first, and so I guess that's okay. .018. So that was HNO3. I'm not sure why I did that one first, but that's the one over here. It's 1 mole is equal to that many grams. 63.018. Didn't leave enough space. And then the NO2 that I meant to do first, nitrogen and 2 oxygens. .01. So 1 mole of NO2, 46.01 grams of NO2. Molar masses. Any questions? How do I convert kilograms to grams? What does kilo stand for? Times 10 to the 3. Kilo makes it bigger. So here I have 1 kilogram on the bottom. I could write 1 kilogram on the top, but that's not going to do me any good. I'm going to write what it means, 1 times 10 to the 3. So this is 1 times 10 to the 3 grams. And then I need to do a conversion at the other end, kilograms to grams. This time kilos on top, 1 kilogram on the top. I'm going to write 1 times 10 to the 3rd on the bottom. What happened with those conversions between kilograms and grams? They cancel each other out, right? So if you're thinking ahead, you can make this a little simpler, but you don't have to. You can just do it this way. So I'm speaking to most of the class, which is probably like, no, just tell me the straightforward way to do it so I can do it. Okay, so we're going to just push this through on our calculators. Remember, when you've got anything with a scientific notation, that it's 1, and then you need to use, it's either an EE or an EXP button. If you're not sure, please ask me in lab and we'll get that straightened out. And that stands for times 10 to the M3. So this would be 1 EE3. So I've got 16 times 1 EE3, and then I'm going to divide by 46.01, multiply by 4, divide by 4, times 63.018, and then divide by 1 EE3. I'm getting, I should have 2 sig figs from the starting number. 21.91 kilograms, which would round to 22 kilograms. Any questions? Stoichiometry is a very important part of chemistry. So, like the combustion analysis problems, if that is just like not making any sense to you, that's okay. Try to get the empirical formulas with the masses or the percentages. You can blow off the combustion analysis. This you cannot blow off. Stoichiometry is going to be through the rest of the course. Very, very important.